So we've fixed the window frames and some pieces of our planar geometry, but now we still need to fix the interior of the building. Now the interior is a bit more complicated because not only is it planar, we want to do a bit more than a simple extrusion. If you were to simply extrude out the different sections of this, then it might be okay, but you would have some overlapping areas that would be better to avoid if possible. For example, if you were to extrude this floor downward like so, and then extrude this wall out as well, then we'd have some overlapping volume in this area here. So we're going to chop up this to help avoid that issue. Another reason for breaking up the interior into multiple pieces is to assist in the results from our fracture. For example, if our Boolean fracture on this building gives us a piece shaped like that, then you'll see that this piece spans across multiple floors. Now, sometimes features like that can be desirable, but you can achieve that by clustering together various pieces, which is a process we'll look at later. For example, if you had Boolean pieces like this, we can set up a constraint system between them so that it's one interesting chunk, but we don't want to be forced to have any pieces that cross floors of the building like this. So we want to make sure that each individual floor's wall and actual floor geometry are individual pieces of geo that we can fracture independently. I'm going to start by dropping in a facet node, and we'll turn on the unique points option. So that will make every individual polygon on our input a separate detached polygon. So none of the actual polys will be connected to each other. So let's display that facet, which won't really look any different in the viewport. But then we'll do a poly extrude, drop that in after the facet, and maybe we'll extrude this out by minus 0.15. And of course we have to turn on this output back option. And this looks like a pretty decent thickness for the walls and floors. However, as we've seen with some of our other poly extrudes, we can have some issues with our normals when we extrude by a negative distance. So we'll apply our usual fix. We'll add a reverse. And when we connect that up, you should see our normals start to pop out facing the right direction. And once again, we have some bad results in our normals there. So let's just drop in a new normal node to fix it. Now let's run an exploded view based on connectivity to see what our separate pieces look like. So you can drop in that connectivity node, and usually I'm running this on primitives. So I'm just going to change that connectivity type to prims, and I'll right click and make that current value default. We'll connect that up to our normal and drop in an exploded view like so. We'll hook that up to our connectivity, and let's see what we've got. Okay, cool. So now we've got our wall geometry and our floor geometry clearly separated into pieces that we can work with, but we'll want to process each of these a bit differently. So I'm going to separate those out based on their bounding box height. Now, in order to get a per piece bounding box to differentiate the floors from the walls, we're going to run a loop over each piece based on our connectivity info. Let me expand our network view a little bit so it's easier to see. And I'll create a for each loop. And we can say for each named primitive. But we don't want this to loop based on a name attribute because we don't have a name attribute defining each of these pieces. Instead, we can just hook this up to our connectivity, and on that for each end, set the piece attribute to class. So if you display the for each begin, you can see it's only processing one piece at a time. So now in this per piece loop, we can drop in a primitive wrangle node and just use one little line of vex to create an attribute that'll store that bounding box info. You can say v at bbox to create a vector attribute called bbox, and we'll say that's equal to this function get bbox underscore size, and then within the parentheses, just enter 0 to look at the first input of that wrangle. And we'll rename this get bbox size just to keep things clean. So now if we go to the end of our loop, we can check the spreadsheet editor to see if this looks like it's working properly. If you go to your prims, you can now see a bbox vector attribute that's storing for each individual piece the x, y, and z overall size. Now after the loop, we can use another split node to separate the walls from the floors. So let's drop in a split, connect that to our end, and within the split we'll say at bbox sub 1, so that's looking at the y value, and we'll check if that's greater than 10. So you can see that's just specifying all of the vertical wall geometry. Now let's create a couple nulls for these. I'll create one for the left side of the split, call that walls, and we'll create another for the right side, and we'll call this one floors. And then we can use the floor geometry to fracture the wall geometry and vice versa. Now our shader tool that we made in week 1 requires us to have a good name attribute per piece of geometry to fracture them individually. So I'll just go through our usual process of creating our connectivity, which is now defaulted to prims, and create a wrangle node, and grab the preset to create names from class. And I'll change the name of this from piece to wall. And of course rename this to keep it clean. And you could actually create an HDA just for setting the names of all of your pieces. Since we do this many times, it speeds things up to create that Vex preset, but it might be worth just a little custom HDA just to do all of your naming. Or optionally, you could even build a destruction utilities HDA that has lots of different options that you can select from for some of these common little workflow things that we do along the way. So now that we have names on the walls, we can do a shader with the floors, but you'll notice that the floors aren't necessarily going all the way through the wall geometry. That won't create a clean cut all the way through. So we're going to need to expand that a bit. So I'll drop in a transform node, and I'll call this transform widen. So on that transform, you can go to the pivot transform, and we'll type in a centroid function. So centroid of input number 0, and we want d_x for the x position. And we'll copy that, tab over to y, change it to d_y, and do the same thing for z. So now if we display that transform widen, and then we change the scale to perhaps 1.1 in both x and z, you'll see that's pushing our floors out so that we can be sure that we're completely cutting through those walls. Now let's drop in our shader HDA, connect our walls to the first input, our cutter floors to the second, and then if you run that, you'll see we're not quite getting the results that we would expect. You would think that it would be chopping the central wall as well, and it looks like if we create an exploded view, looks like it's only chopping these on the side here. Now you can investigate and unlock your shader node to figure out why that might be the case, but upon inspecting this myself, I found that our trim, which removes the areas of the cutters that we don't need, isn't working well on such low resolution cutter geometry. In this case, we can fix it by creating a divide SOP. You can turn off convex polygons because all we care about in this case is the bricker option. So if you connect up our transform widen to that divide, you can see we have a lot more resolution now on that cutter geometry. Then if you pipe that into the second input of the shader and run the shader and display the exploded view, now you can see that all of the walls are being shattered properly. Now I mentioned earlier that you have to watch out for these areas where the walls and the floors overlap, so we're going to remove these skinny little sections that lie within the floors. Now we can use our cutter geometry to group those sections, but it's a lot easier if we pack this geometry first. Now I mentioned earlier as well that packed geometry is essentially like little containers that can store groups of polygons or other things as well, but we'll simplify it and just consider it polygons for now. So you can drop in a pack node, and you can tell this to pack this up into pieces based on that name attribute. So now our 68,000 polys, which contain 720 pieces, you can determine that by middle mousing on the shader node. And under that name attribute, you can say there are 720 unique values. So on this pack, you can see now there are 720 packed fragments. And one useful way for visualizing all of these different pieces is using the packed edit node. So if you drop in a packed edit, connect that to our pack, and display it, you're not going to see anything different by default, but there's this display as option that can change how the viewport displays this packed geom. If you change it to bounding box, it'll create a bounding box for each one of those containers. And that's usually the one I use the most, either full geometry or a bounding box, but you could also display a point cloud, which will be a point for each piece, or the centroid is actually a point for each piece. It looks like a point cloud might be the corners of the bounding boxes perhaps. I usually don't mess with that one. In this case though, we can just leave it on full geometry. And now that our geom is packed, we can use our cutters to group each of those containers. So drop in a group node. I'll set the group name to inside_floor. We'll disable the base group, turn on bounding regions, and select bounding object, which tells you this needs to group by points. So we'll change that group type to points. Connect the pack to the first input, second input to our cutters. And you can see, it might be hard to tell in the viewport here, but it should be selecting, and you can verify this by middle mousing on that group node, 360 pieces in that inside floor group. Now just create a blast node and select that inside floor group from the drop down, and you'll see that removes those overlapping areas nicely. Now we can repeat this process for the floors as well. I'll grab this wall section and drag it off to the side, and we'll copy our naming so that we can name the floors as well so that those will shatter properly. On that name node, we'll change the name prefix from wall to floor, and we'll copy our widening transform and the divide node to apply the same thing to the walls that we'll be using as cutters this time. So if you look at the transform on those walls, now it's pushing it out in X and Z, which is not what we want in this case. Then if we do it that way, then it's just not going to line up with the original position. In this case, we'll set X and Z back to 1, and we'll set Y to 1.1 to make sure that this cuts all the way vertically through all of this floor geometry. However, I'm going to take one extra little step as well to make sure that this is cutting through in X and Z as well. And for that, I'm going to use a peak node. You type in peak, drop that after the transform. And on this, I'll just try a value of maybe 0.04, just to kind of nudge it out a little bit. You can see if I bypass that on and off, it's just doing a slight expansion on that cutter geometry. So now we can run the shader on our floors, connect those floors to the first input, the expanded walls to the second, and we'll run that shader. This time we don't need to do the deletion of the overlap areas. We only need to do that deletion on the walls, not the floors. However, when you're setting up your fractures, it's good to provide yourself as much information as possible about the different sections of your geometry. So I'd like to give these center pieces a different name in case we want to remove them or handle them differently down later in our workflow. So once again, I'm going to do our pack based on the name attribute. And we'll connect that up, and you can see we now have 1,700 pieces. And I'm going to create some geometry along the middle of the building that we can use to group the center pieces. So you can create a shrink wrap, and of course you can come up with different ways to do this if you'd like, but in this case I'll just shrink wrap the geometry, which will essentially create a bounding mesh for that conforms to the rough shape of that geom. And then I will copy one of our centroid-based transform nodes here, paste that under the shrink wrap. I'll change that name to avoid confusion. Maybe I'll call it transform shrink, and we'll set that to 0.2 in X, 1.1 in Y, and 0.2 in Z. So you can see we now just have this core of geometry going through the middle of the building. Now, just like we did before, we're going to create a group node, connect our packed geom to that, and our shrink wrapped core thing to the center. I'll set the name of the group to inside underscore center. Group types points, base group is off, bounding regions on, set to bounding object. And now we have 16 pieces grouped as the inside center portion. Now we want to set a center prefix on the names of these grouped pieces, but you'll notice our name attribute isn't currently available. Because when we packed up our geometry, we didn't promote any of the attributes from the geometry to those overall packed containers. So on that pack node, if you select the name attribute under transfer attributes, now that name is available on each of those packed containers, and we can add a prefix to it after this group. Now, because that name is a primitive attribute, let's make sure that we create a primitive wrangle and connect it to our group. And even though this inside center is a point group, we can still use a point group to specify in our primitive wrangle node. That means only the primitives associated with those points in that group will have this code run on them. So I'll type inside underscore center into that group. And then for that bit of code, we'll say s at name equals the string center plus s at name. So it'll just add that center prefix to all of those pieces. We'll name this center name prefix. And like I mentioned on the wall portion, we don't really need this geometry to be packed right now, so we can just unpack it, since at this point that packing was really only to assist with our grouping. And now that our geometry is all sliced up, let's drop in a merge node to combine our sliced up walls and floors. And then we'll put in an exploded view to see what they look like. And everything is looking all good, although there are some pretty tiny little pieces in here, and we will have lots of little pieces in our fracture, but at this point it's good to get rid of any of these little bits that we won't need. Now I'm going to save the removal of the small bits for the next video, but we can add a little bit of cleanup here. Let's drop in an attribute delete, connect that to our merge, and we can middle mouse and see which attributes look like they're no longer necessary. In this case, it looks like we can get rid of the bbox and the class. So I'll just select those from here, bbox and class. And then let's drop in a group delete as well. And then on that group delete, I'll just say star, and then the caret with the inside group specified. This will make sure that we delete all groups except the one called inside. And similar to what we did with our window fixing setup, let's select all of this interior fixing section here, hit Shift C to put it inside a subnet. I'll call that fix interior, maybe rename the input as well, call this planar interior. We could also add a null to grab this interior later if we need to elsewhere in our scene. You can call it out fixed interior. And then inside that subnet, it's always good practice, as I've mentioned before, to make sure that you add an output node to ensure that this subnet is always outputting the correct thing despite wherever the display flag might be set. And at the end of this fix interior subnet, let's also do a group check for unshared edges. So I'll call it group, unshared, keep everything nice and clean, turn off that base group, turn on edges, and turn on unshared edges, just to make sure that we've output good geometry that we can use for refracturing later. And if we middle mouse on this group, we can verify that there are no unshared edges.